If it's 16 centimeters initial distance for the R2, yeah, that R2 had the attribute of being strong enough to overpower what was going on associated with the R1. So the way to compensate for that, if everybody's held the same, 10 amps, 9 amps, 4 amps, the distances, everything's the same except for R2 varying, you got to expand it. You got to diminish that B field. So it makes sense that 22.5 centimeters being more than 16 centimeters is the right way to go. Okay? That was it. That's all you got to look at vis-a-vis that. So let's look at 37. Okay, they get into this stuff a little bit. Let's talk about it. For number 37, at the instant shown in both sketches, and I'll draw something on that, a positively charged particle travels with speed 356 meters per second, the magnetic field 0.650 Tesla. The angle theta is 32 degrees. Find the magnetic force, magnitude, and direction exerted on the particle in both cases. If the positively charged particle is replaced by a negatively charged particle, same exact magnitude charge, but a negatively charged particle, how do your results change? Okay, so they're giving, I guess, say two scenarios here. So I'll draw it. It's almost easier done than said. But let's take it from there. All right, let me erase this, and we'll go right to 37. Okay, let's see what we can do here. All right, for 37, guys, you show two scenarios. Like I said, this should be substantially easier done than said. Let's remember this and proceed from there in everything that we do. It's a single charge particle. You can do this equation in its own right has a lot of versatility, a lot of application, a lot of real good gut feeling way to look at some stuff as we do this. They are saying in case 1, case 2, I guess you could say, they're saying if there's a B field, now in both scenarios, well, this is of interest. You got a B field here, and you got a charged particle. Charged particle here. And here we go. Let's take it at an angle here. Here's the charged particle. It's moving with velocity v vector, and this is that. And this angle right here, the angle to the B field is theta. And the other scenario is kind of similar. They're still giving you the theta here. They're just saying the B field's kind of behave, that there's a different, same magnitude B field, in fact. But what's happening is things are coming out, so I don't know how many of these I'm going to draw you guys. This means the B field's coming out of the board in all directions. I mean, in all places. I simply can't draw all places, but it's coming out that way. The particle is still charge Q, still going with velocity v vector, and that's basically the scenario here. So here we go. For A, find the magnetic force, magnitude and direction exerted on the particle in both cases. If the positively charged particle is replaced by a negatively charged particle, how do your results change? Okay, so it shouldn't be too bad, guys. What we have here is, so let's just go this scenario then, basically. Case one, let's, again, can we visualize what's happening correctly? Can we use the right-hand rule correctly and get an idea of what we're talking about? Well, I said this is the case. Simple as that. I guess they're going to tell us a number of things here. FB vector this is Q vector. I'm sorry, this is QV vector. QV vector cross B, right-hand rule. Let me just cross. You know, there's things you can do with your fingers as well. How to do this thing, but I'll do this. Let's cross this thing. Let's cross. So go here, go that way, cross. QV cross B, bam. Your thumb goes into the board. QV cross B, thumb into the board. Okay, it's into the board. If this is X, if that's Y, that's negative K vector. It's in the negative K direction as we do this thing. So let's see if this actually spits this thing out okay for us. We are told it is millicoulombs. That's 10 to the negative 3. We got this, 356. That is the velocity. This is all MKS system units. I wrote it a little differently. I mean, I wrote the V hat, B hat. That's fine too. Basically, guys, you're just setting up how you're gonna take this thing to completion here. You've got this right here, and you know, I'll tell you what. Let me jump the gun a little bit when we do this. You've got it in my notes as well, guys. You should be able to, let me just jump a little bit past the notes sometimes, because I know you can always go right back to the notes. If you do this whole song and dance, you guys, you should be looking at here it is. Time out. We said it's going to be K hat somewhere. Right? Yes, but I did not like the way it goes into the page. So you got to kind of, yeah, this is sort of true. No, there's no sort of true. It's true, but it's really, we already kind of agreed it was going to go, at the end of the day, it's going to go into the page. So when you're doing this thing. So what do we got here? When you actually do it, you're going to get 1.90. K hat times N for newtons. You got to throw the negative on there for this guy to be kind of for the application to actually work. So looking pretty good. Looking pretty good there. All right. So we got that. That's B. I'm sorry. That's the force associated with the B field. Case 1. Case 2. Let's see what they got here, guys. Let me look at it first and foremost. This isn't as bad as you think it is. This theta, it plays a role and it doesn't, I guess you could say. It actually does play a role. Actually, what am I talking about? So what we got here is the B field comes out this way. QV is that way. B field this way. Here we go. Let me go QV cross B. Bam. I think it's going to have a force associated with it. Right there. Well, actually, shouldn't have gone right there. Right here for this guy, and then not him. We already got him taken care of. Okay. So the chocolate, I at least want it, right? What's going on here? All right, so there you are, guys. I mean, that's how this one's going to play. Let's try it again. The B field is coming out this way. This guy's going that way. They're perpendicular to each other. QV cross B, bam. It's going to be perpendicular to the plane made of the B field, made of this particular parcel of B field. The B field here and the QV here, that plane right perpendicular to it, that's going to be the scenario. What does that mean? Well, it means a lot of stuff. If that's theta, if this is 90 degrees, this is 90 minus theta. So there's a lot I can say about that too. I mean, that's 90 minus theta. Let's see what we're talking about here, guys. In this case, if you were gonna go there, let me tell you what. Let's save a little bit of time. I hope. Let's look at, if I was going to do case 2, it is identical. Case 2 is going to be the same kind of situation, sort of. This was case 1. For case 2, let's talk about magnitude here. It's going to be the sine of 90 degrees. Okay, I already, we delivered that speech. It's going to be a sine of 90 degrees. This is going to be where it's at. And so case 2 is going to be a different situation, but let's keep it like this. Should hold up pretty good. When you actually do it, you're going to get FB on this one. Well, FB associated with case 2. With case 2, FB is going to be 3.587. It's bigger than the other one. Why is it bigger than the other one? Well, the other one had the sine of 32 degrees associated with it. This had the sine of 90 degrees associated with it. There's got to be a difference. And it is. It's reflected here. It's not magnitude 1.9. It's magnitude 3.587. Quite a difference here. So you got this. Where is it located? I mean, we already told it. Hey, look, guys. Let's make this really clear. This is 32. This right here is 58. 58 and 32 is 90 degrees. We said it was going to be 90 degrees. It's going to be this at 58 degrees south of east. Yeah, I mean, it's true, absolutely true. If you had to, kind of an interesting scenario, this guy's, if you get this component right here, you get this component, it's going to be as big as the magnitude of what this guy was, because it's going to be it's going to be the cosine of 58 degrees, which is the same as the sine of 32 degrees. So it's going to be as big as that, and then this guy's going to be something, and then this part's going to be something different. Basically, if you get the cosine of 58 degrees and the sine of 58 degrees, you can get the components. And they're talking about components too. In this case, not a big deal, but still, you got to be careful. You got to go 1.90 in the positive direction. I told you it was going to be as big as the other one. And the other one's going to be negative 3. Well, it goes down. It falls down, you guys. The cosine of 58 degrees is the same as the sine of 32 degrees. Yeah, the sine of 32 degrees, when I had it here, spit out the answer of 1.9. So it's going to be the same 1.9 magnitude. It's only going to be in this direction. Then there's going to be also the component this way. It's in the XY plane, and this is what you would get at this point. So that is what we were talking about regarding that. That was problem 37. There are two more for this chapter. Problem 72 and problem 92. They're both real gem. 92 is a real gem, I think. You know, it's a really beautiful problem. So let's keep going. Okay, 72, okay, they great problem as well. I mean, for problem number 72, it says a straight conductor, again, this is all chapter 30, you guys. Chapter 30, number 72, a straight conductor between points 0 and P has a mass of 0.50 kilograms and a length of 1 meter. And carries a current of 12 amps. It is hinged at 0 and is placed in a plane perpendicular to a magnetic field of 2 Tesla. If the conductor begins from rest, determine the angular acceleration of the conductor due to the magnetic force. Ignore the effect of gravitational force on the conductor. We're assuming there's no gravity present, guys. And there's just there's a current going through it. They're not really specifying a whole lot here. I think this is just given to us for the sake of actually being able to do a problem like this and really examine some things here. So let me draw some of what's happening here. So I'll give us a little bit of insight. So they're saying so here's O and here's P. There is a current. You know, they're not getting too much into specifics here, guys. As far as you know, where this scenario would occur, but for our purposes, we've got something here. We're going to determine a few things based on the data that they're giving us here. All over the place on this. So let's see here. So this whole thing down here. This is. They kind of use their language very explicitly, I guess. And they're doing this. That just means the B field, let's write it, let me just write explicitly what's going on here. The B field is equal to 2 Tesla as they have shown it to you. So B vector equals 2 Tesla as they have shown it to you, going into the board like that. Okay, so it's a little. No pretty way to do it, I guess, but there it is. So we're looking at something like that, you guys. There is no gravitational field to be accounted for. For our purposes, there's no gravitational force to be accounted for. We're just going to look at what happens vis-a-vis the current, vis-a-vis the magnetic field, and what's associated with the magnetic field and the current, the force associated with it. So let's see what we can say about that. If the conductor, okay, if it's hinged here, okay, determine the angular acceleration of the conductor due to the magnetic force. Determine the angular acceleration, okay. a lot going on here. It's kind of taking us back a bit, but it's good that they're doing so. So let's see what we have. All right, let's write a few things on this. Let's see if we can remember. Was a little too. I mean, what I said is correct on this thing, but let me actually kind of explain that indeed it's correct. There's a lot here. You can say. What I want to say, just to kind of give some background on this thing at least. I told you this thing's got a lot of mileage. This thing's got a lot of mileage right here. You can do a lot of stuff with this. One of the things you can do with it is QV vector can be IDL vector cross V. You can make the QV vector IDL vector. Kind of go there. And this ain't bad, because I got a couple ideas here. If the current I is going this way, and the B field is going in, if the B field is going in and the current is going that way, why don't you cross product? Go IDL cross B. B's going in. B's going in. So IDL cross B, boom. This thing is going to be pushed. It's going to be forced upward somehow. Yeah, let's talk some more. IDL is this way. IDL is this way. B is that way. They're perpendicular to each other. Whenever you do a cross product of two things that are perpendicular to each other, in terms of magnitude, you guys, you got this, or maybe, that's not the best way to write that. Let me write it. It's the same thing, of course. Yeah, I mean, it's you can kind of say that, but I mean, you'd have to in this particular circumstance, you'd have to be doing more or less an integral. This is more of if this is really short, that's going to be really small. I mean, so I don't want to. If you want to be a little more, I mean, if circumstances are right. This is really the analogy. These guys right here. One implies the other in the right circumstances. And certainly, and right here too. I mean, this is also true. I mean, this is really, this does a lot. You can do a whole lot with that. But it's got to be a differential element to that. So you got to come right down to here. Sort of jumped the gun on that in the notes. If you divide by DL on each side, yeah, that makes sense. That makes sense, and then you can also write it like, whatever. Forgive me for going around in circles with you a little bit here, guys, but so one follows from the other. One follows from the other. I just happen to put the DL back this way. Let's talk a little bit. I guess I'm going to look at this thing in terms of torque. And torque is, if you allow me to be really cavalier about it, torque is associated with force, associated with distance. I mean, let me put this here and then kind of not go too crazy with it, but there's the association of force. It gives it implies, you know, in terms of a magnitude, it's force times moment arm times the sine of theta or the sine of phi, whatever it is they're using. Okay? Well, we already kind of said you know, this is the way I did it here. It's okay, but maybe this is more explicit. The force everywhere here. Now, I've completely obliterated what I was, right? But we know what I is anyway. We got this. We got this. In all circumstances, they are perpendicular. So if you do a cross product, you're talking about the sine of 90 degrees in some sense. And this is I, and we said I was going to be 12 amps. And because the sine of 90 degrees is 1, it's going to be F times R. So torque is going to be F times R. Differential torque is going to be, torque is F times R. Well, yeah, differential torque is going to be dF times L. Times the, now the L changes. The L varies. This is really important. L is greater than or equal to 0, less than or equal to 1 meter. It is a continuous phenomenon. I'm going to get the torque on this thing at every single location. At every single location, for example, right here, that's L. Right here, that's another L. L is going to vary. L is going to go from 0 to 1, and we're going to figure out what's going on vis-a-vis all that. Okay. If that's the case, let's do it. Let's talk about it. If this is all that, and we already said that this guy is what it is, let's see what we have here. D tau is dFL. Notice it's not, the force here is a differential force associated with, I guess it's a differential force associated with how much current is actually present here when we actually do something like that. So we do it, or actually a differential element of length. The current is the same, but there's only a small differential element of length right here, which means there's not that much charge moving that fast. Whereas the length of this thing is the lever arm. This is a lever arm right here. All the way to here is a lever arm. All the way to the very end is a lever arm. There's infinite number of lever arms. All of them are either, they're between 0 and 1 meter long, and it's as simple as that. And wherever you want to go, you find, you know, this is an actual lever arm of length L. Further on, this is another lever arm, also length L, a different length L. This is a function, and it varies. And I'm going to have to do a, you know, and that's what we're going to do in an integral. So let's see what we got here. We got d tau is this. And we said d tau is going to be dF times L. dF varies, as we said. dF is going to be IB L. That ain't a big deal. The deal is what makes it happen, guys. The IBDL is the force. So when we look at it, maybe a little, you know, you allow me to backtrack a little bit, guys. The force is IB dL. That makes it a small force. Then you're multiplying by L. To make the integration, I don't know, a little more palatable, I guess you could say, just switch around the dL and the L. It doesn't really change anything. So we got this right here, you guys. Remember,